When I give a talk, I get used to asking questions because they're like trying to get any of the questions at the end of the conference. The secret.
No, we're gonna get started soon, so find your seats. So this is Papers Below San Francisco #3. So I'm glad to see new faces. Thank you so much if this is your third. I recognize a few of you that have been here. Everyone, thank you. Pretty much like we're here to learn about academic papers and interesting research. And today we have Bruce from Fastly, and he's going to talk about Bimodal Multicast. Food, drinks over there. There's a restroom in the back, and then if you need, there's like more downstairs. And also, I've been asked by my marketing department to announce that we have a conference coming up in August. It's not October, it's August. So I'm just called Distill. Yeah, if you're looking for something to do in San Francisco, it would be nice. Without further ado, it's like no words that I'm using that are much significant. I give you Bruce, and yes.
Hi, so I'm Bruce Spang. As Emmett said, I work at Fastly. I'm also a student at UMass Denver. So today I'm going to be talking about this great paper called Bimodal Multicast. It was written by Ken Birman and a bunch of other people from Cornell in the late 90s. And the paper is designed to do this algorithm called reliable fragments, and I'll talk a little bit about it in a while. I'm also going to be talking about a system we built on top of Bimodal Multicast at Fastly, which we call PWLSF. So here's the general way the talk's going to go. I'm going to talk a little bit about the problem we had, and about why we started reading this paper in the first place. I'm going to talk a little bit about the papers we looked at in the process of building this system. I'm going to talk a lot about Bimodal Multicast and the behavior of the algorithm and some of the guarantees and the other things about Bimodal Multicast. And then I'm finally going to talk about PWLSF, which is the system we built on top of it. So before I get into any of that, I'm going to talk a little bit about Fastly so you can sort of understand the problem we were trying to solve. So in case you missed Andrew Gross's amazing talk last month, Fastly is a content delivery network, and I'm going to talk a little bit about it. So the way it works is we have a bunch of servers spread around the world, and our general goal is to make a website faster. So normally, we would have this user, this blue circle in Australia, and they might want to go to a website. Let's say it's this star over on the east coast of the United States. So normally what you would do is you would make this long request across the world to get to this website, and then you would get the response back. So with Fastly, instead you would go to a server, let's say in Sydney, that's very close to your home. And maybe we would have the website already cached on that server. If we didn't, we'd go and we'd get it from the east coast of the United States as before. And then we would store it on our server so that the next time someone asks for it, it would be much faster. So this works pretty well, and it works great actually. But we have this problem that we'd like to solve, which is we'd like to be able to update a piece of content across all of these servers globally. So here's a bunch of reasons we might want to do that. So suppose we have some sort of news website, and the news website would like to cache a lot of it. One of the things they might like to cache is the homepage of their site. So because lots of people visit this homepage, and it doesn't change all too often, maybe on the order of half an hour or an hour. But the problem with caching a homepage in the sort of classic CDN model is that you have to post new articles to that homepage. And you'd like these articles to become visible very quickly to all your users. So we would like some way to be able to update this homepage across all our servers to, say, add new articles. We might have a social network. And again, we'd like to cache all of the content on the social network. So we might have a page like this one, which is pretty cacheable, except for stuff like this. We have avatars all over this page. And so we can cache those pretty easily, but occasionally someone will want to update their avatar. And so we'd have to go through this site, and we'd like to update all of the pages that have this avatar. We don't want the user to be browsing through this site and see some of their old avatar and some of their new avatar. And then the final example we have of this caching validation problem is sometimes we have a customer who allows users to host their own content, and sometimes the users don't host particularly legitimate content, and they receive some sort of letter from some lawyer to take down the content. And so we would like to be able to remove this content from our network so that it doesn't appear on the site anymore. So the way that we go about solving this problem is all we do is we tell all of our servers when a piece of content changes. Then these servers throw out the old content, and the next time they get a request for the content, they'll go all the way to the original website, and they'll get the new content. So this is the problem we tried to solve, And so the first way we tried to solve this was pretty naive, and it was with this central service. We had this API that was accessible, and it talked to this server in Virginia somewhere. And it worked a little something like this. We had the central service on the left-hand side, and all of our cache servers on the right-hand side. And we would receive some request from some customer to update the content, and we would broadcast that request out to all of our servers. All of the servers would then tell us that they got the request, and we would be good. We know the request went everywhere. But sometimes we would send a request, and the request would get lost. So after this happens, we would wait for a little bit, and we noticed that we don't receive any acknowledgments from the servers. And so we would try and resend it. So this time the message got everywhere, and we'll get an acknowledgement from all the servers, and we'll be done. So this central service works. Like, this solves our goal of sending a message to all our servers to update this piece of content. But it doesn't work particularly well. It's not a particularly reliable way of solving the problem. We're sort of assuming that all of our users can reach this central service, and that this central service will even be running. And this generally didn't happen. The other problem was that this was a sort of high latency way to solve the problem. So suppose we had one of our users that was publishing some content, and they happened to live in Hong Kong. And maybe all their users were also in Hong Kong. And so all of their content was stored in Hong Kong. And so it sort of doesn't make sense for us to send this, this purge, this update to the content, to some server on the east coast of the United States, and then back to Hong Kong. We have cache servers in Hong Kong, and it sort of makes sense for us to use them. So this is the second way we went about solving this problem. We decided to have cache servers broadcast these updates themselves. And so this is a much better solution. It's much more reliable. It's much more likely that one of our customers will be able to reach one of our servers than it is that they'll be able to reach some central server. And it's also a lot faster because the cache servers tend to be much closer to our servers. But this also, right, so here's the way it would work. We would have, again, it's a similar model as the central service, except instead of this being a central service, it's one of our cache servers. So we would receive a request, we would send it out to all the servers, and we would receive a response back. And this works pretty well, but it has a problem. Every time we send a message, every single one of the other servers in the network will send us an acknowledgement. And so this works fine when you have 5 or 10 servers. But when you get up to 100 or 1,000 servers, it means that every time you send a request, you get back 100 or 1,000 responses. So even if you have a really fast system that can handle something like 100,000 or 1,000,000 requests per second, you can only do something like 100 or 1,000 requests per second. And so that's sort of unacceptably slow. So this led us to believe that this is actually a hard problem. We can't just sort of guess at these algorithms and come up with something good. And so we decided to start looking at research papers and try and find a good way to solve it. But as it turned out, there's this really nice field of research called reliable broadcast that solves this problem pretty nicely. So the general problem for reliable broadcast is you have a bunch of servers, and you have a message, and you'd like to send the message to all of the servers. So there's a bunch of, that's a pretty general problem, and there's a bunch of different applications of it. This is true for stuff like stock exchanges, where you have some quote, and you have a bunch of clients, and you have to send the quote to all the clients as quickly as possible. It's true for stuff like control systems, where you have a bunch of machinery, and you might want to signal them all, like turn off or turn on. It's true for updating configuration on servers. You might want to do something like update some firewall rule across all of your servers. And as it turns out, it's useful for caching validation, because we want to send this message to all of our servers. So when we started reading these papers, the first sort of papers that we came across were this class of problems known as atomic broadcasts. And this is stuff like the Paxos algorithm, where Zookeeper has a way to do this. And generally, these algorithms are characterized by these very strong guarantees. They have this guaranteed message delivery, which is that if you send a message, it will either get to no servers, or it will get to all servers. And they tend to have a total order. That is, if some server processes 2 messages in any order, then all other servers will process the 2 messages in the same order. And so these are super great guarantees when you're building something like databases, but it didn't matter too much when we started thinking about them. We don't particularly care about the order between purges. It's totally fine for us to purge one customer's content before another customer's. They're pretty much independent of each other. And we also realized that we don't really need that strong of an adequacy guarantee. We want to deliver the purge everywhere as often as possible. But once in a while, we might lose a purge, and we can sort of deal with that from a company level. We would like it to be extremely rare, but maybe sometimes some server sort of freaks out for like a week at a time, and it might not get a purge, and that's sort of okay. So we kept reading and trying to find something that fit our problem a little bit better. And we came across these classic papers called best effort broadcasts. So instead of this sort of super strong guarantees of the previous atomic broadcast, these sort of algorithms just try very hard to get a message everywhere. They can't guarantee that a message will go everywhere, but they'll do their best. So there's a whole bunch of algorithms that do this. The first one that I know of in this class of algorithms was this scalable, reliable multicast. Then there's bimodal multicast, which I'll be talking about shortly. There's Plumtree, which React uses for configuration. And there's Sprinkler, which is a pretty neat paper by Birman. And there's links to all of these in the slides, which will be online later. So now let's talk about bimodal multicast, which is one of these best effort algorithms. So bimodal multicast has two goals. The first goal is this sort of best effort delivery. It wants to deliver a message to all servers with some high probability. And the second goal is we want some sort of predictable performance. And I'll talk a little bit about what that means later. So here's the general algorithm for bimodal multicast. It's split up into two phases. There's a dissemination phase where we try and get the message everywhere. And there's an anti-entropy phase where we deal with the cases where it didn't get everywhere. So first, the dissemination phase. In this phase, this happens immediately after we receive a message from one of our customers. And we unreliably broadcast this message to all servers. There's a whole bunch of ways we could do this. We could do something like IP multicast if that was available, or you could do what we do, which is just loop over all the servers and send them each HTTP. And so the goal of this phase is just to get the message to as many places as quickly as possible. So the actual best ever delivery guarantees come from this anti-entropy phase, so periodically this anti-entropy phase runs, and every server picks another server at random and sends them a digest containing all the messages that it lists out. This other server receives this digest. It compares the digest it received to its own digest and tries to see that it's missing any messages. If it's missing some messages, it asks the sending server to resend the message. The sending server then resends the message. The receiving server receives them. And then at the end of this anti-entropy phase, the receiving server has all the messages that the first server did at the beginning of the phase. And so this runs at regular intervals over and over and over again. And the goal is to get the message everywhere. So here's an example of how this works. We have three servers, A, B, and C, and we have three messages, 1, 2, and 3. So we have this dissemination phase where A sends out messages 1, 2, and 3 to servers B and C. But for whatever reason, server B doesn't receive message 3, and server C doesn't receive message 2. So then the gossip phase runs, and every server picks another server at random. And it just so happens that server A picks server B and says it has messages 1, 2, and 3. Server B picks server C and says it has messages 1 and 2. And server C picks server A. So these servers will receive their digests, and B will notice that it's missing message 3 and ask A to resend it. And C will notice that it's missing message 2 and ask B to resend it. So then the message is resent, and after this runs, all servers will have all messages. So this is the general algorithm for bimodal multicast. Before I go on, are there any questions?
The gossip phase needs to be pretty reliable, right?
Yes.
How do you ensure that?
So this brings me to my next slide. So the gossip phase doesn't need to be reliable. We'd like to have some sort of guarantee that this thing actually works. But it's not obviously the case that it works just by seeing three servers, right? It's sort of nicely worked out when we sort of manually picked which servers will gossip with each other. But maybe when we have a bunch of servers, some server will just not receive a gossip for a long period of time. So here's another example that sort of attempts to address that. Each of these circles represents a server, and there's 100 servers. The white circles are servers that have not received a message yet, and the green circles are servers that have received a message. So this is immediately after the initial dissemination phase. And for whatever reason, 4 servers have received the message, and 96 have not. And so we're going to run the gossip phase over and over and over again, and each server that has the message is going to pick another server at random. And if that server doesn't have the message is going to be recovered. So let's see what happens. We can see that the message is going everywhere pretty quickly. And with just a few rounds of gossip, the message gets everywhere. This sort of gives us a better sort of indication. It's just a little more that this thing will actually work. we scale it up to more servers. But it'd be sort of nice to have a better guarantee than that. It would be nice to put something in production that actually works and doesn't just like, we sort of think it works based on this experiment. So to address that, the paper has a whole section in which it like quantifies the algorithm. And one of the things they managed to predict about this algorithm is the expected percent of servers that will receive a message after some number of rounds of gossip. So here's a graph of that expected percent. Along the x-axis is the number of rounds of gossip that have occurred. Along the y-axis is the percent of processes that have received a message. Initially, just 1% of processes will have received the message. And at the end, nearly 100% of processes. That is, almost all processes will have received the message. So we can see that around round 5, it's about 25% of processes. And then it starts growing very quickly. And after 10 rounds of gossip, there's about 97% of servers expected to receive the message. So this indicates that this works pretty well. And this is a pretty reasonable guarantee, even if it's just best ever. So that's the best ever delivering guarantee goal for Bimodal Multicast. And the other goal is this predictable performance. So let me talk about that a bit. So first, let me talk about what predictable performance isn't. So let's go back to our example with the distributed acknowledgement algorithm that we gave at the beginning. And again, we have our cache server on the left sending messages to all the other cache servers that are on the right. Except this time, one of the servers is going to be running very, very slowly. Maybe the load spiked on the server up to like 100,000, and for whatever reasons, it's just not processing messages right now. So as before, we'll broadcast out the message to all of the servers, and we'll receive an acknowledgement. But this time, because this slow server is running slowly, we won't receive an acknowledgement. So then we'll wait a bit, and we'll try and resend the message. But because the server is running slowly, we could keep trying to resend this message, and we could retry it over and over and over again. And if there's a whole bunch of messages that we have queued up to retry, and if the server doesn't respond for a long time, we may be trying to resend like thousands or hundreds of thousands of messages. And so that means that we will start to slow down as well. So now not only do we have this one server slowing down, this other server is also starting to slow down. And then this might continue for a little bit, and these two servers might start sending messages of their own. And now this server is running slowly, so it won't acknowledge its messages immediately. And these two servers might also start running slowly. And so there's this weird situation in this algorithm where we have one server that's running slowly, and all of a sudden, all of the rest of the servers are degraded and are also running slowly. And so we would like to avoid this in a good, reliable broadcast algorithm, like Bimodal Multicast. So the way it does that is with this concept of independence. So a server that's behind, instead of recovering from one server and putting a lot of load on that one server, it'll spread its recovery out from many servers in the cluster. So it'll pick a bunch of servers at random, or other servers will pick it at random rather. And a bunch of servers will sort of collaborate in recovering this one server. So this helps a lot with the slowing down. Another thing that helps a lot is Bimodal Multicast has this optimization where they limit the number of retransmissions in every one of these rounds of gossip. So a server that is very behind will only request some smaller portion of messages than it possibly could. And a server that's ahead will not send all of the messages that it possibly could when a server asks. And so this prevents us from sending all the messages at once and denial of service attacking this one slowing server. So even with that retransmission limit, there's still sort of this problem where some server could run behind for a little bit and then try and catch up and start processing messages, and it could request a bunch of messages. And even with this retransmission limit, it could request enough messages to back it up and slow it back down again. And we would like to start recovering these messages at a later point when the server is back and running normally. So the way Bimodal Multicast deals with this is this idea called stop failure detection. And the general goal of it is to just ignore servers that are running slowly until they start running quickly again. So the way we do this is in every digest we send, we include some round number. So the first time we send a digest, we say it's round 1. The second time we say it's round 2, and so on. When a server receives a digest and tries to compare that digest to the messages it knows about, it sends back the round digest that it received. So after round 1, it says, hey, I need these messages, and this is in response to the digest from round 1. The server that receives this digest, this request for messages, will compare the digest that it received to the last digest it sent. And if they don't match, it means there was a bunch of time between when it sent the digest and when it just received the digest. And so then it will just drop the request for messages on the floor because it assumes that the server is ready to load. And it'll wait for it to start responding to these gossip requests. So that's piece of failure detection. And so the goal of all of this is to have this predictable performance. And so the way the paper evaluates this is by running some experiments. And so what they do is they have a traditional algorithm, sort of like the one I gave at the beginning. And they have bimodal multicast. And they have a cluster of servers, all processing messages at some rate. And they pick a few of these servers, and they cause them to sleep for some % of the time instead of processing messages. And then they see what happens to the throughput. So here's a graph of the results of this experiment. Along the x-axis is the perturb rate, which is the % of each second that a server will be sleeping. And along the y-axis is the throughput. So the first thing is the traditional algorithm at the perturbed host, which is this line of squares that goes down here. What we can see, sort of as we would expect, is that as a server spends more time sleeping, it spends less time processing messages, and the throughput goes down. And this is also true for bimodal multicast. Bimodal multicast is this triangle line along here, and it will also get slower as it spends less time processing messages. Sort of strict, like expected. But the concerning behavior for the traditional algorithm is what happens at the servers that aren't running slowly. So that's this circle line that's going right here. And we can see that as some of the servers in the cluster start to slow down, the rest of the servers in the cluster also start to slow down. So that's not desirable. But bimodal multicast is this star line at the top. We can see that even as the other servers in the cluster are being perturbed, even as they're slowing down, the servers that aren't affected are still processing purges as. So this is indicates that bimodal multicast actually does have this sort of predictable performance. So what all of this means is that even though bimodal multicast is best effort, even though it doesn't have this sort of very strong delivery guarantee, it still works very, very well. There's still a very high probability that a message will be delivered everywhere, and we can put a number on this probability and know what we can expect in production. And there's also very predictable performance, even when servers are running slowly. So we saw all of this, and we decided that it would be a good idea to implement bimodal multicast. So we did that, and the system we built is called Powderhorn, and it's our system for doing this hashing validation across all our servers. So as it turned out, Powderhorn was a sort of interesting project to build, and it wasn't particularly like your sort of normal web application, because all of the logic was in how we handle failures. The sort of normal case for bimodal multicast is you receive a message and you send it out to all your servers. But that's very straightforward, right? You just loop over the servers and you send them a message, and most of them receive it. Where bimodal multicast gets interesting is in cases where the network starts to fail, right? Where we start to request messages from other servers, where we have to insert these limits in the number of messages we're requesting. And so this was sort of interesting to try and expose during development, so we could put numbers on these limits. And so the way we did that is with this fantastic tool called Jepsen, which is written by this guy called Kyle Finsbury. And it's a tool for testing databases, specifically when they're exposed to network problems. So the way it works is you have 5 virtual machines, each running the server, and they're all communicating with each other and sending messages back and forth. And then you can manually initiate network problems between these virtual machines. You can cause total network partitions, you can cause partial connectivity, you can cause high message loss, or you can cause lots of latency. And so with this, we were able to sort of expose these failure cases in the Powderhorn and see how it dealt with them. So this was very useful for getting an idea that we had actually implemented bimodal multicast correctly. So once we did that, we decided to test some more reasonable approximation of the number of servers we would be running on. So we went to EC2 and we got 200 virtual machines. And so we got a bunch of very mediocre virtual machines, the M1 mediums that are very slow. And the reason we did this is to test this sort of this slowing down behavior and see if there was actually anything here. And we also had to test this sort of failure case, but with 200 machines, it wasn't particularly practical to impose network problems between them. So we built this tool called Avalanche, which allowed us to inject these network faults at random. So it's available online if you want to check it out. So after this, we had a pretty good sense that Powderhorn actually worked. we were able to put it in production without problems related to bimodal multicast, which was really nice. So one of the problems we encountered when building Firewall was this problem of garbage collection. So we have these message digests that we're sending around between all of our servers. And every time we'll say something like, I have messages 1, 2, 3, 4, and 5. And as we receive more and more messages, we'll start to talk about more and more messages in these digests. And so if we didn't get rid of messages after some period of time, we would start to have these very, very large digests. And we'd start to using up significant amounts of bandwidth if we started sending around 1 million messages in each of these digests. So we need some way to start throwing out old messages to keep the size of this digest small. So the way the Bimodal Multicast paper recommends doing this is they recommend keeping a message for 10 rounds of gossip, and then after the 10th round, just throwing the message away entirely. And this is sort of a little bit surprising, but it makes sense when you look at the math. And so if we look at the math, again, the expected percent of processes after some number of rounds, we can see that even if just 1% of servers start with a message, after 10 rounds, about 97% of servers will receive the message. So it turns out that this keeping a message around for 10 rounds is a pretty reasonable guarantee. But the problem is that we deal with the problem is that this graph has a 0% message loss. It's a sort of reasonable approximation when we're doing this math, but we don't actually deal with that in production. We deal with real computers, and as it turns out, real computers are horrible. We see this sort of high packet loss, and we see network partitions, and we see them all the time. And so we would like to not assume that we're going to have 0% packet loss with our algorithm. We'd like to assume something more. So here's another graph. This is the expected percent of processes after some number of rounds again. But this time, there's a 50% message loss going on. This blue line is 50% message loss. And this black line is the same one as before, with 0% loss. And so what we can see here is that after 10 rounds, less than 40% of servers will have received a message. So we see these sort of problems pretty frequently, maybe once a week, maybe a little more than that, maybe a little less. And so we would like to be able to deal with them and get purges to more than 40% location. So the main problem, the main reason that we were throwing away messages after 10 rounds was the limited size of this digest, right? And this is because I suspect that the paper was implementing them as a list of message IDs, right? They were saying, I have messages 1, 2, 3, 4, and 5 from this server. But the thing we realized when we were building Firewall is that this digest doesn't have to be a list. It can be any data structure we want as long as it represents the set of messages that we know about. And so what we eventually decided to use was a set of ranges of the messages that we know about. So instead of saying, I have messages 1, 2, 3, 4, and 5 from the server, we'll say, I have messages 1 through 5. And so in the normal case, when a server has received all messages, this means that we can represent some huge number of messages with just 2 integers. We can say something like, I received messages 1 through 1,000,000, or 1 through 1,000,000,000 from this server. And the amount of bandwidth we'll use stays constant. So this lets us represent these very large amounts of messages, and we can keep messages around for much longer. So what we do in production is we keep about 1 gigabyte worth of messages around, which works out to be about a day's worth of gossip. So let's go back to the expected percent of gossip, the expected percent of processes that have received a message after some number of rounds. But this time, instead of just 20 rounds, we have a full day's worth of gossip, something like 80,000 rounds of gossip. And on the y-axis, again, we have the expected percent of processes. And this time, instead of 50% message loss, we have 99% message loss.
At any given point, are you going to do the ranges, something that you could make adaptive? Like I said, at any given point, have you even considered, because basically what you're doing is you're compressing the digest. Can you just like start playing with type of digest, or actually that would completely break down everything because people are expecting a digest on a given point? Can you pre-gossip like the range of the digest and then start sending things depending on the type of traffic that you get hit, or basically you have the same types of requests where the range is static and you don't ever need to expand because maybe...
Right, so we do run into situations where there is packet loss, and so we start to get gaps in these intervals. And so we will record that as you'd expect. We'll say something like messages 1 through 5, and then 10 through 20. And then when a server receives that, it can tell that there's this gap of messages that it doesn't have. That answers your question.
I don't know if I asked it correctly. So what I was like saying, right? So you have a bound of things that I'm like, except from now on that I'm going to know that a digest is from 1 to 1,000.
Mm-hmm.
But the range of 1 to 1,000 is rather arbitrary. It means that you specify that this thing equates to a day of traffic. Are there types of traffic where maybe you want to have more? Is it more bursty, where maybe a day is not enough,
right,
or is too much, or is too little?
Right. So the reason we have a day is based on the current throughput numbers,
Mm-hmm.
And so if that started significantly increasing, we have to change that.
Oh, but you change it, yeah.
The message.
Okay.
That's the thing we have to do, but it's not super. Yeah, so back to this graph. It's got the expected percent of processes that received a message with 99% packet loss. We can see that after a day, there's something like 99 points, some huge number of nines, expected number of processes that received the message. So this is a very reasonable guarantee when there's extreme network problems. We're comfortable saying that, give us our purge and we'll deliver it everywhere with this sort of high probability. So now let's talk a little bit about the sort of behavior we see from PWLSF in production. So one of the things we care a lot about is the end-to-end latency for this sort of caching delegation. We want to care about the number of, the amount of time it takes for someone's desire for content to be updated to actually appear on all the servers at the new content. So the way we measure this is between the number of milliseconds between the time a server receives a message initially from the customer and the time some other server on the network receives the message. So as it turns out, Bimodal Multicast normally succeeds in this dissemination phase. So normally what we see for the latency is based entirely on the network latency between servers. So most of our purges arrive in New York, London, or San Jose. And of those, New York is the most centrally located. So what I have here is a graph of the 95th percentile purge latency. Along the x-axis is the latency, and along the y-axis is the density. Basically, the frequency that this latency appears. And this is for a number of different data centers: New York, London, San Jose, and Tokyo. So New York, as I was saying, is the most centrally located. And so it receives almost all of its messages in under 50 milliseconds. London and San Jose are pretty close to the rest of our data centers, but they're pretty far from each other. So latency for them is about 80 milliseconds. And then Tokyo doesn't really receive many purges itself, and is pretty far away from the rest of our data centers. So its latency is something like 150 milliseconds. So as we can see, during normal operation, when we don't lose too many messages, purge latency is basically the network latency between servers. But much more interesting things to look at are what happened when the network isn't working too well. So when we were deploying PowerPoint, we had to go to all of our servers, install PowerPoint, and punch some holes in the network so it could communicate with each other. But at one of these data centers, we messed up this firewall configuration, and we caused a few of the servers in the data center to not be able to communicate with the outside world. They could only communicate with other servers inside the data center. And so we sort of expected this to be a problem, but it turned out to not be a problem. So along the x-axis, so on the left-hand side here, we can see the throughput at both the affected and the unaffected servers during this time. The affected servers are red and orange, and the unaffected servers are blue and purple, I think. And so the throughput during this time was the same, both for the servers that could communicate with the outside world and for the servers that couldn't. And so what this means is that the servers that could only communicate within the data center were able to recover messages from inside the data center. So over on the right-hand side, we have a graph of the purge latency during this time. And this big spike here is when we caused this firewall problem. And the sort of surprising thing is that it only spiked up to about 10 seconds. And so the servers inside the data center were able to recover messages after about 10 seconds. So that was pretty neat. It sort of confirmed that this thing actually worked as we were deploying it. There was another problem we saw pretty recently. We have a data center in New York and a data center in London. And we saw this network problem between the two data centers where the New York data center couldn't communicate with the London ones. But both of those two data centers were able to communicate with other data centers like Frankfurt. And I think London was also able to communicate with New York or something weird like that. So again, we thought this would be a problem, but it wasn't really. On the left, we see the throughput. And it's basically the same for London, which is this blue line, and New York, which is this red line. There's not a significant difference between the two data centers. On the right-hand side, we see the number of recovered messages over time, which is the number of messages that we recovered in these rounds of gossip. And this large increase here in the blue line is the time the network partition happened. And as it turns out, this maps almost exactly to the number of purges that were sent by New York in that same time. And then this big red spike here is when we finally pulled New York out of rotation. So again, it was sort of neat to see this thing actually deal with network partition. Here's another example. This one happened last weekend when I was preparing a talk. I went to go and look at the graphs and see if everything was okay, and it totally wasn't. We were seeing sort of high packet loss in the Asia and Pacific regions. They were having a lot of trouble communicating with the United States, and we were seeing something like 20 to 30% packet loss, and it lasted for like 4 hours. And again, this actually was not a problem. It was just sort of neat because I could take these graphs and sort of put them in the slides real quick. Because the throughput stayed approximately the same, both for the blue servers that were affected and the red servers. Sorry, the red servers were affected and the blue servers weren't. Over on the right-hand side, we see the number of messages recovered over time, and it got up to like about a third of our total traffic at that time. But it still worked very well. So the final example I have was a few months. So we had these customers that have their own networks, and sometimes we'll send them servers that they can put inside the networks, so that we have cache servers closer to their origin, and it'll take load off their servers. So one of these customers, a few months back, experienced a pretty large denial of service attack, and their network became almost completely unreachable. We couldn't SSH into our servers in the network, we couldn't ping them, and they seemed to be totally dead. But we were looking at the power burn graphs during this time, and they were working, like it seemed to be working surprisingly well. So on the left-hand side is the throughput during this time. The blue server is a normal one of our servers outside this network that wasn't affected. And the red server, this red line here, is one of the affected servers. This big spikiness here is when the denial service actually started to take out the network. And we can see that it was definitely affecting power. Right? The purge throughput was significantly different during that time. But what's sort of interesting is that if you squint a bit, you can sort of imagine that the average for all of these spikes is about the same as the unaffected server. So even during this sort of insane network conditions, this server was still managing to recover messages, keep up pretty well with the server that wasn't affected. Purge latency during the problem spiked up pretty high. It was about 10 seconds and sometimes got up to about a minute, but it was still able to recover these messages. So what all of these examples show is that this bimodal multicast algorithm is great. We generally don't have to worry about our purging system failing, even when we're having network problems. And so this is real nice, right? Because we can be working on a talk, or like, wanting to go out with friends or whatever, and the network could break, and you can be like, cool, like it'll take care of it. So that's really, really nice. So that's all I've got. Thanks. So the slides will be online at this website. There's also the graph of the expected % of servers over time, and a simulation and a link to the bimodal multicast paper. Are there any questions?
How do you tune the frequency of the gossip rounds?
So how do we tune the frequency of the gossip rounds? We're just doing it every second, and we haven't really tuned that at all.
That works and works.
Right. So I guess if we were to tune it, the things we'd have to consider are the network latency between our data centers, which is at the highest something like 200 to 300 milliseconds. So we couldn't do it any faster than 200 to 300 milliseconds, and we're giving it like maybe double that just to allow it to go back and forth.
Right. What about, you mentioned the message IDs. Mm-hmm. Are those global, or are they per pair?
Right. So the message IDs are per server. They consist of the server ID, the start time of the server, so we don't get duplicates, and then a monotonically increased integer.
How does this scale up as the number of servers increases?
No clue.
I could go
Why do you find it couldn't do faster than the actual latency between the servers? I mean, you could do just well when it's randomized. I mean, you wouldn't take advantage of messages until they'd already been populated, but.
Right. The thing that I would be concerned about is you have to send this digest and then this other server has to check out what it has and send a response, and then you send the messages that it wants. So you have this forward, back, and forth, right? And so if you were to do that faster, or if you were to initiate that faster than the round trip time, you might run into situations where you just kept adding on more these gust runs.
It might be a little less efficient, but if you think you really needed it, you can really max out.
Yeah, we might be able to, and I think it's actually configurable. We want to do it.
Right.
How do you handle membership in these gossip rings?
Right. So that's sort of a tricky problem, and we don't do it super cleverly. We just have this sort of central service that will pull, we'll fetch a list of all the servers, and then we'll load them in. It doesn't change too frequently. We add data centers like something like once a month or once every few weeks. So it's totally fine to have this.
So the Bimodal Multicast just chooses servers at random. Are you ever going to take kind of note of the server topology that you have? Because presumably you have like 3 servers or a few servers in London, and then a few servers in New York, and then ones that are further away. Will you look at that to see whether you can like choose, like send digest to the other ones in London to see if you don't have to transfer them over your long links, or also look at ones further away?
Yeah, so we've thought about that, sort of like gossiping with our local neighbors more frequently, because that would also let us gossip much more quickly than a second. But it's much more complicated, and this has turned out to work pretty well.
I'm curious as to why you guys would go with Plum Tree or Sprinkler. Like, what's better about Bimodal Multicast?
So the reason we didn't go with Sprinkler is because it was super new, and we met in late December. We were working on this before that. That's pretty much the same reason for Plum Tree too. I haven't tested Plum Tree or Sprinkler, so I can't say for sure. I would be interested in seeing how it actually says.
If the network's working just fine, on average, how long does it take, or how many rounds of gossip does it take for a message to be everywhere, like in general?
Right, so normally the message gets everywhere after the dissemination round, and we only see packet loss there during usually like normal packet loss, something like less than 1%. So usually the message either gets everywhere within that first dissemination, or it takes a round. So
right, so in most cases, it's just like a round trip from where the push happens to all the machines.
So the paper talks about biasing for most recent messages and then eventually giving up if you can't reconcile.
Yes.
It sounds like here you're pretty much tuned to like, oh, we don't ever have to give up because we keep supplemental long enough. What happens if you truly lose it?
Then we truly lose it.
And does purge just happen later based on the TTL? Like the world doesn't end if you lose a message?
Right. So ideally, people wouldn't be setting like 1-year TTLs to be able to get rid of it, or we'd be able to get rid of it when we sort of restart branches across the machines or something like that. But yeah, it's totally possible for us to just lose the thing. That would be unfortunate and be a pretty weird scenario. But as the slide showed, it's really
Somewhat off topic, but how do the cache servers authenticate to one another for those messages?
So what we do is we sign and encrypt the gossip messages back and forth between them. So we have like a set key and stuff like that. Like they ship out with the config. They can send messages.
Is that a global one or per server?
I think it's global.
So you mentioned that by the time that you were storing these like billion long logs and sending them back and forth, that it was taking up a lot of bandwidth. So you just did this like quick trick to send the intervals as opposed to the actual ones. Of course, if there's something like a little bit less regular, like any type of like variation over things, then it can start getting expensive again. Did you guys just try like gzip or maybe in particular a compression algorithm that was more designed for these sorts of long tens of zeros or ones? Or like why did you come up with something homegrown?
So we didn't try anything like that, but I don't know enough about compression algorithms to predict the bounds on this. But I suspect that we can do better with like 2 numbers or a few more numbers than that.
Yeah,
just to compress intervals.
you would think that like you could do something well with the compression item that was tailored to what you're doing, but in general, the way they all work is that they look like if you have a message which always either has 7 zeros followed by or like a single 1, then it just like says, it compresses all those 7 zeros into just right, and it's doing the service function. But of course, there are ones that are better for radio card accounts. But maybe like you've solved the problem by doing it, but you get an extra 10% compression.
Yeah. Yeah, we could also compress the intervals that was sent out. But I think one of the things you hinted at was that we can still run into situations where we get a bunch of intervals. Like if we're seeing very high packet loss and we get something like that really messy. Right. And so the way we deal with that is we limit the number of intervals that we'll send every round of gossip to something like 32 unique packets or something like that. And then we can we will cycle through the different intervals to include in that message. Right. So we'll still get the recovery, but not like cap out the menu.
So the message payloads in your system are very small. What if you were dealing with messages that were like multimedia files or something that were quite large? Would the same system work unchanged, or would you have to tweak things?
We would definitely have to tweak it. So the main reason is that when we respond to messages, we pack them into PP messages again, just because it's pretty convenient. And we would have to do something different, like probably use TCP for the gossip runs, some of these larger files. But we wouldn't actually have to change the digest algorithm, because that's just there.
So you mentioned whole new data centers coming online at once periodically. Is there much skew in when various servers will find out about the new batch of servers? And if so, how does that affect things?
So it depends. We pull from new config about once a minute. So they learn that pretty quickly. But there is definitely a partial sort of custom membership at some point. And we actually had a bug at some point in the past where if a server received a message from a server it didn't know how to just crash. So that was real cool because we enabled the server and then we started seeing all these alerts and it's like, what's going on?
Did you, I noticed that you didn't do the optimization of multicast on repeated retransmission. Was that something you didn't find that was necessary in this case?
Is more like you didn't want to bother with it. The main reason is we don't have FP multicast available, so it's a little bit expensive to send the message to all those groups. Just we'd like it to just be fast.
So you mentioned a few other ways, or sort of like industries where you would be using this type of algorithm. I was just wondering, since you guys have had such success with this for cache and validation, have you experimented with using this for the original population of cache that the person's server doesn't have to get hit as many times to start with? I mean, maybe you don't have enough servers that they even care.
Right. So we actually have another way of solving that problem, and that's we route requests through other cache servers. So we'll have, say, one cache server only talking to the customer's website, and then all our other cache servers will be talking to it. And then we'll only have that one server making requests.
But don't to some extent you still have some of the same problems that you were running into originally, where you have this graph where there's one critical node that sort of gets hot and things are activated.
There is, but usually we don't have that sort of behavior. Right? Normally it's like, if it's a very popular piece of content, usually it'll be in whole caches at the edge.
Right.
And if it's a new piece of content, it'll.
Yeah, if you're having problems with it.
Yeah. It's fair time.
Can I follow up your answer to that?
Yeah.
So the way it actually works is that all the other servers are talking to a small group of load balance servers, and then those servers in that group are actually talking to each other as well. Right. So only one of those or two of those potentially will make requests to the origin, but they're still not the single point of failure in there.
Any other questions? I guess that's it. One more thing that Tyler would kill me if I didn't mention. If any of this sounds interesting, you work hiring. So come talk to me or Tyler, or go to this website. Thanks.
What?